live. Okay. Hey everyone. Yeah, I was going to share my journey, the experience of trying to decipher what's going on with this audio amp chip for the Mega 65 R3. And yeah, like any apparently small thing you look into, you always dive in and find other things along the way. So yeah, there's plenty of other stuff I learned along the way. So yeah, firstly, apologies. Yeah, it's going to be very long-winded and boring, probably for many. And yeah, sometimes you investigate something small and it turns out to be a big can of worms. And yeah, most of these details, I think your regular Mega 65 user isn't going to care about. But if you're interested, you can stick around. Like maybe you're the sort of person that likes to know what's working under the bonnet of the machine, or maybe you've heard about the R3 board. You can add internal speakers if you want to. So maybe you're curious about that possibility. Or maybe you're just somebody that loves details. There's plenty. And yeah, maybe one day you might also want to investigate these speakers and this amp chip yourself. And yep, it's a lot of info. It took about a month, sort of divided with a long break waiting for parts. So there was a lot to learn for me. And yeah, I wouldn't worry about understanding everything. Just get the gist and that's enough. And if you ever find you need to dive into these topics yourself, you can always rewatch this and focus on the details later. What I'll cover, I'll share why I'm looking into this, why I'm choosing to talk about this, and my follow the white rabbit journey down the rabbit hole, and clearing up my initial misunderstandings, and on the way I learned some things about the audio mixer, the advanced view and the simple view. And yeah, there was a big long journey of going through different parts of the code base, the config, hippo source, VHDL, and schematics. So a good chance to sort of guide you through that. And yeah, it was a chance to learn more about this amp chip itself. I had to buy some parts to install the internal speakers, which took a while to receive. And even after doing so, it still didn't work. So I had to find out why not and dig some more and then have some reasons and fixes to share, and then I can share the demo of it in action. So firstly, why look into this? Well, there was a community member, Hojo, that I knew of. He installed the internal speakers already for his R3 board, but they never worked for him no matter what he tried. So yeah, I thought it'd be a fun project to get a chance to debug this area of the project, which I'd heard about but never used before. And yet I'd also heard about this AMP chip, and yeah, there was a chance to learn about that. And also, yeah, I really appreciated Hojo is the one that's created all these beautiful new front covers for our manual. So yeah, I think he did a lovely job there. The user guide, the basic reference, chipset reference, developer's guide, and complete compendium, or what we call the Mega 65 book, the big one. Yeah, so this was just my way to say thank you to him. After all his effort, he did all this stuff for free, and yeah, I'm happy to do this in return for him if he wants these internal speakers working. Hopefully, we can get it working for him. So why did I choose to talk about this? Well, as usual, I'm going to forget all this stuff. And yeah, truth be told, I already have. I mean, making these slides helped me remember, and trying to wrap up the project helped too. Yeah, the big problem for me was I had to wait months for the electronic parts to arrive. And in that time, yeah, my head went blank. It became a little bit hard to sort of put everything back in my brain again. But yes, doing this presentation has helped me remember some of those details. Not all of it, that's for sure. And there was a PR I had open with some fixes to this, and that's been closed and merged in recently, which is good news too. So yeah, I was hoping these slides could sort of help convey to the reviewers too, what my train of thought was, and the reasoning behind my solution. But I think I conveyed that in the PR already, and it's all good. But it was also a chance to share with the general viewers how did I go about investigating this? Where did I go about digging? And yeah, maybe it can help others to, if you want to investigate a matter that's important to you, where would you go look? Where would you get your shovel and dig into? And so, yeah, it might help you, give you some ideas too. And yeah, where to look, where to dig, yeah. And yeah, some people have never gone, digging in this realm, so it's a chance to show them those pointers. And it's a big, ecosystem. This code base has grown over 10 years, spanning over, you got some assembly files over here, some C code over there, some VHDL, some Verilog over there, some schematics, some PCBs. It's a lot to get your head around, so it's nice to have a few starting points to know where to dig within this big code base. And so what I'd recommend, if you're going to do this, take some notes along the way, jot them down what you've learned on this day or that day, just to help you remember. Because just like me, I imagine you're going to learn things and just forget them and get overwhelmed. The next day you'll learn some other stuff and forget the stuff from the previous day. So yeah, good to take some notes along the way. Be good to share your notes with others. I'll be trying to do more of that too myself, because others might investigate the stuff you're investigating. They might find it helpful too. And take a look at other people's notes, and also on Discord forums and blog posts, and the Meg65 book. The PDF has a lot of info in it too. Yeah, they're all good starting points. And don't hold back from asking questions too on the Discord server. So, but yeah, my follow the white rabbit journey. So it started off with this audio amp setting here. This in the config page. When we power up with the Alt key and press 1, we get these config screens where we sort of configure different aspects of our system, which SID chip we want. Let's say, do we want to swap the stereo channels around, or do we want stereo mono? Yeah, and there was always this peculiar one called audio amplifier on or off. And yeah, it was a mystery for quite a while what this was. I think some people in the community thought it was like some way to boost the main volume of the system. But people would try that, turn it on and off, and it wouldn't make any difference. So no, it wasn't that. Some people thought it was purely for the headphone socket. So, then we tried that and turned it on and off. Didn't make any difference there. So it wasn't that either. So it turns out this switch here is to switch off an audio amp chip, turn it on and off. But what audio amp chip? This was like a chip that was unique to the R3 generation of boards. They had an amp chip that was going out to two connectors. So this amp chip over here, and these connectors, the speaker left and speaker right connectors. So yeah, the intention was, the amp chip takes that sound and amplifies it, sends it out to your internal speakers, which you could plug in there. But yeah, what did these internal speakers look like? And it was two fellows on the Discord server that spotted Mindrail and Dr. Vulcan. They were watching one of ATPM's videos with Deft, and they noticed in the video that he had opened up his Mega 65, and lo and behold, he had installed these speakers. So I think that's the first view we had of somebody installing them. I recently added the internal speakers to my R3 too, and that's how my install worked out. In addition, I added a few capacitors to sort of help out. I think there was some heating issues to get the DC bias out of that. But yeah, back to this config screen, this audio amplifier setting. What's it actually doing when you say off or on? And yeah, it's writing your choice into a part of the SD card, what we call sector 1 of the SD card. But then who makes use of those settings? So, okay, you write down a setting onto your SD card, but sooner or later somebody has to read that and do something. You've decided this, you've decided that. Where's the actual doing of it? All right, this is your decision. Hear me, I'm going to implement your decision. And that's done in what's called HippoBoot process, which I've learned the term for that is the HippoBoot process. And so it's going to load up those choices that were stored in sector 1, the settings that you've decided, I want this audio output, this stereo channel swapping, or this audio amplifier. And then it's going to configure the hardware to adhere to your chosen settings. So what's a sector though? So for those that aren't familiar with, at least in our case, it's a group of 512 bytes on your SD card. So sector 0 would be the first 512 bytes. Sector 1 would be the second set of 512 bytes. Sector 0 tends to get called the master boot record. In our case, not always, but in our case it is. And sector 1, this is something unique to the Mega 65. That's where we stored this config info. All your choices you make in the config screen are stored in the 512 bytes of sector 1. So how does the config save these settings? Well, okay, there's some logic for if you really want to dig into it. I don't know if we want to. You could follow this GitHub page and get to this Mega 65 config.s file. And you could watch the process of how the settings are stored into a location. Another file related to it is this mega65 config.inc, and this one is more a list of these settings that will be shown on the config page. So at least in this current study, I was curious, what is the details of this audio amplifier setting in this mega65 config.inc file. And taking a look at that file, I could sort of decipher this group of bytes and words that had been dropped in there in the table. And each of them was like a field describing what this setting would do. So breaking it down, the first byte here, byte 20, was describing what kind of input type. There's different types of inputs on the config screen. Type 20 meant an on-off style option, something you could toggle on and off. And the next line was config table offset 0003. What that's trying to say is that in sector 1, the third byte, or well, depending on how you count, if you count like 0, 1, 2, 3, you might say it's the fourth byte. It's saying that that fourth byte of sector 1 is going to equate to this audio amplifier setting. It's where this is going to be recorded to be on or off. So later on, somebody could read sector 1, look at that fourth byte and say, it's 1, so amp is on, 0, it's amps off. But what's this next field underneath that? There's this 01 here. It says bits for testing or setting. So this setting bit field thing is, it's, how do I describe this? In order to turn this amp setting on or off, yes, it's true, you need to modify sector 1's byte 3 or byte 4 if you count from 0, but only it's bit 0, so not its bit 1 or bit 2, bit 3 of the byte value, only bit 0. I think they did that so in future you might want to sort of stuff more bit fields into a single byte. Another setting goes into bit 1, another setting goes into bit 2. It doesn't matter so much for this byte 3 because I think byte 3 only consists of the audio amplifier, but that's what that field is for anyway. But if you did want to take a look at sector 1, if it helps get your bearings, you can use the Mega65 FTP tool and tell it to dump what's in any sector you like. So I gave a little example of that. If you start up Mega65 FTP and you type in, sector 1 or whatever sector you like, it'll dump out those 512 bytes. And you could look at what is the fourth byte, in my case, 0, 1, 2, 3. And you can see I've turned on my audio amp chip. I've turned on bit 0 to be 1. So yeah, that can help you get your bearings with this thing. And you could study other settings and see what does byte 0 represent or 1 or so on in the same fashion. And this is Mega65 FTP can even let you poke that sector byte directly. You could, sometimes I would do this, I would type commands into Mega65 FTP, say poke. This has 3 fields. First field is which sector you want to poke into. So I say sector 1. And what offset into sector 1 do I want to poke into? So I've got different reasons like turning on some other settings on and off with other bits. But let's say in our case, we want the audio amplifier. If we did want to poke it this way, we'd say poke sector 1 at offset 3 for us. And we'd poke it with a value on the third field of 1 to turn it on or 0 to turn it off. So yeah, if you did want to cheat that way and not use the config, you could. I've done that in the past for when I'm using Zemu, which can't get to this stuff. But yes, what about the details of, all right, we've saved that into sector 1, these choices, but how does Hippo actually apply that settings choice? And so in that Hippo boot face, there's a part that's in this assembly file, syspart ASM, which I'll point to here for folks that want to visit it. And that has a bit of code that does this activity here. But to get my head around what's happening here, why this DE03? The 03 part relates to this offset, the third byte or the fourth byte if you like. So it is kind of reading that from the sector. But what you need to understand is that this part, this area, DE00 all the way to DFFF, at this point in the Hippo boot process, it's holding the contents of sector 1. So yeah, so DE000 is the 0 byte, DE001 is the byte 1, and so on. So if I read DE03, that means I'm reading the value that was saved at offset 3 in sector 1, which is the audio amplifier setting. So the next step we see after that, so the D03 sector 1, yeah, the byte at index 3. This ANDing of 1 is just saying we just want to focus on bit 1 of this value and not any of the other bits. So it's sort of filtering out the other bits. And then we see it's applying it to some IO register, this audio amp control thing, and saying, all right, this on-off value, let's force it on the hardware. Let's turn that amp chip on, or let's turn that amp chip off. So yeah, during this hippo boot process, that's where these settings get enforced, all of them. So yeah, this term hippo, I thought now that we've mentioned it, it might be a good chance to clarify this term hippo, because I think there's a bit air of confusion about it, even for me at on the onset of this. So firstly, what is hippo? So our first experience of hippo is that startup process you see when you boot up your Mega 65. So that can give us some bearings on one aspect of what it is. But that's just the startup phase, and probably this phase ought to be called hippo boot. And but this phase it can be seen as akin to Amiga's kickstart phase, this kind of bootstrap process that starts up the OS, gets it ready for the OS to run. So yeah, you can see this hippo boot phase of hippo is a bit like that too, a bootstrap process that prepares the system for loading up. In our case, it's the C65 or the Mega 65 ROM. But hippo is more than just that hippo boot process. Yes, it does that job, but it has another duty too. And you even get hints of its other duties inside here, because you hear this term at the top here, hypervisor. That's worth digging into later. And you also get a clue of some of the services that Hippo is doing for you, like it's mounting DI81 images. You see it's mounted this Mega 65 D81, successfully mounted. So that's a service that Hippo is providing. If you ever want to mount an image, yes, you ask Hippo, can you mount this image for me? And you can see it's also can load up various files from an SD card straight into memory. So that's this line up, loaded the Mega 65 ROM. So yeah, you could ask Hippo at any time in your code even, please Hippo, look at the SD card, see that file there, put it into memory over here. Yes, you can ask Hippo to do things like that too. So, but what to call that startup process? Is it Hippo boot? Or another term I heard was hiccup, and that caused some confusion for me. So it's a chance to clarify that. So like initially I thought this hippo boot up process phase was called hiccup. And why did I think that? Because of that ick term in there, H ick. And I thought when I saw ick, it equated to kickstart, which is very synonymous with that boot up process. But no, I'm sort of, it's dawning on me that aspect of the name is a bit of a red herring when it comes to the term hiccup. And how it came about was in the early days of the Mega 65 project, they did use the term kickstart for the boot up phase, but then later on they were concerned that that's a very exclusive Mega term. My headset conked out again. So yeah, they were worried that term was very Amiga exclusive, so they transitioned it. At least there was this commit comment here that said, yes, we've renamed kickstart to hippo boot, well, hippo boot. So yeah, that helped clarify things for me. But yes, in those older days, there was this kickup M65 file, and you could drop that as an optional on your SD card. And when you did, it would upgrade the logic of your boot process. So that would, during the development phase, it would save you the need of having to rebuild a new core. Like if you have building a core used to take about 1 hour, I think, but building a kick-up file with an update, a repair or a fix, and you want to test it, it was a nice, easy way to sort of update your sort of boot up phase and check if it worked. But yeah, at least in that era, the name Kickup was trying to convey that, we're upgrading our kickstart. So this is a upgrade file. But after that name transition, changing the K to a H, it became known as Hiccup. So the H part, yeah, that's trying to convey hippo. But the ick parts, for me at least, is now a bit of a red herring, because now we're not just upgrading the boot up phase, we're upgrading all of Hippo, and Hippo is more than just the boot phase, it's also the services that Hippo provides. So yes, it's no longer just an upgrade of the boot up phase, it's an upgrade of all of Hippo, boot phase plus its services. So this unfortunate connection now is the word hiccup really means hippo upgrade or hypervisor upgrade, if you like. But this was another question mark on my mind. Is hippo a hypervisor? Is it really a hypervisor? Which leads, what is a hypervisor? And that comes, that's a term that's coming out of the virtual machine world. And it's a layer of software that manages your PC resources and it tries to share them with multiple virtual machines. So your machine, let's say you're on a Windows PC and you've got your CPU, your memory, and your I/O, and then they add your virtual machine software adds this hypervisor layer, and it tries to share those resources with other virtual machines that are running on your machine. So you could have a Linux virtual machine that borrows some of your CPU and memory and I/O, and you could also have another sort of flavor of operating system, let's say OS2 running in another VM, also on your Windows PC, also borrowing some of your CPU, memory, and I/O. And this hypervisor layer of software is kind of managing and supervising the sharing of these resources. But is our Hippo really doing anything like this? And from what I read historically, there was a blog post from Gardner's. It had aspirations to one day maybe become something like this of sorts. You could read his blog post there on virtualization and task switching. And yes, he had aims of letting our hypervisor manage system resources to share them between multiple tasks. So not multiple virtual machines, but multiple tasks. So his example is like you could switch one like an assembler or a game and another as a game. So he would have the Mega 65, its CPU, memory, I/O, its Hippo with its boot phase and its services, but some other sort of facility here that would let you sort of share CPU, memory, I/O resources with task 1 and some other way to share them with task 2 and to flick between them nice and easily, which we don't have something like that as yet. But yeah, the reality for now is that Hippo only does those first two things. It initializes the hardware stuff on the boot up process there, and after that point, it doesn't take any kind of proactive managerial role of CPU or I/O or memory or anything. Maybe one day it could, but presently no. And it more acts like a library of services that's awaiting for the software. You need these sort of extra level of services that the ROM doesn't provide. You can ask me and I'll do it for you. So for me, no, Hippo is not a hypervisor as yet. Maybe it could be one day, but as yet, no. So for me, I see it more like a hyperkernel, at least the services side. Our ROM has a kernel that provides some sort of capabilities that the Mega 65 and the C65 are aware of. But there's other capabilities that it isn't aware of that you have to ask the Hippo to do for you, like mounting an image and so forth. So yeah, I see, yes, the Hippo is more of a hyperkernel that's providing a library of services beyond what a normal kernel can do. But then again, with that concept of switching tasks, I mean, I suppose you could use the freeze slots as a task switcher. But if you read through Gardner's post, that wasn't the way he envisioned task switching. Um, he envisioned, yes, having some sort of small OS perhaps at this Hippo layer that could, allocate memory and I/O usage and such to those different tasks and swap between them. That was his goal there, which, maybe one day that will come about. And yeah, I remember this Discord discussion sort of pondered that term a little more if you want to discuss it further or learn further. But yeah, why am I caring about Hippo and getting distracted by it? Yeah, because yes, I wanted to get to the bottom of what this audio amp setting actually did. And I guess some of that journey relates to Hippo. It's this config menu, but is this config menu a part of Hippo? But not really. It's another standalone program. But during that Hippo boot process, it can call it. Like if you press Alt and F1, then yes, this other software will get loaded for the config to do its job. So, and yes, you recall when we save these settings here, they get saved your configuration choices to sector 1 of your SD card. So, and when the Hippo boot process starts, it's going to apply those users settings onto the hardware. And that's at this phase, you'll see, and yeah, all those settings, audio amp on, all that stuff is applied. So what's my actual problem then with this audio amp then? So yeah, we're looking into why Hojo's internal speakers didn't do anything. He could flip it this way, that way. Nothing's coming out of his internal speakers either way. And I confirmed on my side when I checked sector 1, I could see that this setting is saved and loaded successfully. I can even step through that hippo boot code and assure that that IO register is being turned on and off. But the way it's applied, it's having no effect on this amp chip. And so looking back at that hippo boot code in syspath, we saw this application of the setting, get the first bit, apply it on there. And the I wanted to know what exactly is this IO register it's writing to, and it was at this address, D6FE. But the other thing I saw in the VHDL is that, nowhere in the VHDL was this IO register being listened to. So this was doing nothing. So that was my first clue. And probably in the past, I guessed that maybe this register did exist, but fell off the radar or dropped off somehow. So that meant starting to examine the VHDL and sort of see what I could find there. And see what related to this D6FE and the audio amp chip. And I did see some ideas in this file, audio mixer VHDL. Inside there, I spotted some FE, not D6FE, but FE, enough to sort of give me a sort of clue that maybe they're related. And I saw in there, okay, an amplifier enable signal will equate to the first bit of the data being written. And I thought, okay, that's a good match. But yeah, did this FE here relate to D6FE? And it turns out it kind of did, at least in the intent, but it kind of didn't, as in this isn't the right place to look for D6FE. This FE, where they're looking for it here, relates to something called an audio mixer coefficient, which requires a bit of explanation too. But the audio mixer has 256 of such coefficient values, and these aren't mapped into the memory mapped IO space. So you won't find audio mixer coefficients in addresses like D6FE or things like that. They're not in our memory map at all. To set such things, just for curiosity, you have to do so via two IO registers. They have a D6F4. This one is where you set which coefficient index, you want to read or write to. And out of the 256, you have to say, I want to write to the third one or the 200th one, and you put that number in here. And at this F5, that's where you either write the data you want to send to that coefficient or read the data that's already in that coefficient. So then I thought, well, if that's the way they've set it up right now, it's an odd place to put an audio amp on-off setting. But what if I were to turn that audio amp chip on via this mixer coefficient? Would it genuinely turn on? And from what I saw, I think I hooked up my oscilloscope that time onto that pin of the audio amp chip, and no, or actually no, I think I saw the line go on and off, but that in itself I think wasn't enough. I think I gave a call with that fix to Hojo, and he said no sound coming out of it at that stage still. So yeah. So yes, I feel like this was an accident. I think the intent here was to genuinely put the IO register at D6FE, but somehow it accidentally got confused with the putting it in the audio mixer coefficients instead. And later on, I repaired that. I put it back outside to this D6FE, and of course, so anyway, back to this. To confirm, audio amp chip on/off should have no relation to mixer coefficients, and it deserves its own unique IO register bit field. Yep. But yes, anyway, since it was accidentally put there, it did get me curious. What are these audio mixer coefficients? And I'd put them like that. They're a bit like a volume knob that decides how much of an input will be mixed into the final output. And you'll see on the advanced audio mixer view, there's this very overwhelming view it has of every single coefficient, and it's quite a hard thing to decipher. I've even already started putting annotations on it, and I'm going to put more annotations, which will make it even worse for you, I'm sure. Shall I show them now? Or maybe I'll start with the current annotations first. So we're seeing that many of the rows are sources or inputs coming in, and the columns are outputs that will go out of some, I don't know, source like a speaker or to the headphones and such. But maybe I put notes here as well on my. Okay, so the extra annotations I put here, all these things in yellow here, 0, 1, 2, 3, 4, 5, 6, 7, so on. These are the mixer coefficient indexes. So, if we want to write to one of them, this is the 0th coefficient, that's the 1th coefficient index, and where we saw here the amp chip on off has accidentally been put here in the FE, or the 254th coefficient index. Yeah. Okay, I'll let the bullet points take over to help me out. So the rows are our inputs to the mixer. So here you can see the SID left channels coming in, and oh, there is an exception. Okay, yeah, that is an input coming in. Oh, the phone, I guess that's the cellular modem. I guess all the screechy noises. Bluetooth, is that some sort of headset thing? I don't know. Line in, not too sure. Maybe that's a headset. But the digis are the, like, used to play the mod files and such, audio samples. So those are inputs coming into the mixer as well. Microphone, that's a bit confusing. Maybe it's a playback of what's being coming in from the microphone, another microphone. And a lot of them have left and right for inputs separately. The OPL chip. But this master one, I think, is an exception. Yeah, I said this. It is not an input into to be mixed, but it is the final volume control for the output channel of that column. So let's say for speakers left, yes, these inputs go into speakers left. They get mixed to the degree of what these coefficients are. But when they're mixed, then the final volume level of speaker left is decided by this master setting. So it's not really an input, but it's a final volume setting for the whole output channel. So yeah, so the columns are our outputs that are coming out of the mixer. So we got the sense of that. I've got speaker output here, modem output here, Bluetooth output, and headphones output out of the headphone jack. So all of these inputs get mixed to varying degrees. How much of the SIDs do you want to your headphones, or how much of the digis do you want to your modem out? Or you make those decisions like that. And each coefficient value is actually a 16-bit value, which is the easy thing to overlook initially, because we called these coefficient indexes of 0 and 1. So, but they actually are a coefficient together as a 16-bit value. So to read a coefficient, we need to read out two values from that pair of I/O registers we saw before. So here's an example. If we want to read out how much of the SID left audio, the input, is going to get mixed into the speaker left, which speaker left should really say HDMI left. I think speaker's a bad term for it, sorry. So yeah, if we want to know that, then if we recall those two registers before, D6F4 and D6F5, so yeah, if we want that, we'd have to poke the address, the coefficient index of 0 into D6F4. So we're picking this one here, and we'd also then peek what's inside D65F. So for this coefficient index, what is its value? We find that value from D65F5, and yeah, we'll get BE back. And then we have to do the same thing for this coefficient index 1. So we have to poke D6F4 as 1. We're interested in this coefficient index now. And we'll peek the value from D6F5 to get the data that's in that index 1. And that's also BE. So the real value of the coefficient index here is this 16-bit value. So you'd have to add the two values you peeked together. You'd get the high byte and shift it 8 bits across and add the low byte. And you'd find the 16-bit value of the amount of SID left going into the speakers left, or HDMI left, is BE. And so what you'll find is that if this value is a bigger number, that means you've turned the volume knob higher. And if that value is a lower number, like you see the amount of SID right going into the left HDMI is a lower number, 40. So you can say you only hear a little bit of SID right in your left speaker, and you hear a lot of SID left in your left speaker. And alternatively, for the right speaker or right HDMI, you're only hearing a little bit of SID left in your right speaker, but a lot of SID right in your right speaker or right HDMI. So looking at that, should the amp chip be turned off via this coefficient value at index FE? No, it doesn't make any sense for an amp chip to be turned off via a mixer coefficient setting. So that was just more evidence that this was just an oversight, a mistake. So while I was in this mixer turf, I guess it was a chance to explore how does the simple mixer relate to the advanced mixer. If you've looked at our freezer menu, you'd know that we have two of these sort of views of here, and how do they relate to one another? I think it doesn't come across so easily. And what I found after digging into the simple mixer, oddly, it's been hard coded, this view on the left, to only match what's on the headphones output. So yeah, what you're seeing, these bars here, they're all the values, well, not all the values, but yeah, they're from this column, the headphones column only. And so really, probably to help the user of the simple view, it probably should say something like this is the left output channel of headphones, or right output channel of headphones. So I actually won't go there yet, but to get a grasp of it, let's say what they said here is SID34 is this much. Oops, sorry. So what's that equating to is SID34 is, or SID left, written as SID left here. So you'd go over to here, and I believe this is the headphones left. So that's this is trying to show the BEBE value there. And oh, sorry, that one here. And this left digi. So left digi is this digi L here. If we go over here and see what it's set to, it's also set to BEBE for the headphones left. So yeah, it's these rows on the simple mixer are kind of like just cherry picking which inputs, some key inputs to focus on. And the master here is the overall master control of that headphone final mix. Yeah, so that's what's going on there. But if you want to take a look at why it's been hard coded as headphones only, you can look into this freeze audio mix file, and in there you'll see this function draw simple mixer, and it's picking coefficients and then drawing those bars, picking the next coefficient, draw a bar, and so on. And you see the kind of value it's picked are all hard coded in that range we've got on here. So if you recall, that range of the headphones is this range from C0 all the way to FF, and everything here has been hard coded to that range. Um, so probably the code in there should be updated one day to not be hard coded, and let people sort of, with a key, sort of a left arrow or right arrow or something, to slide between. I'm looking at headphones now. Let me change this to view what's on the speakers or the HDMI, and fiddle with exactly the output you want to fiddle with. But yeah, as yet it's hard coded to headphones. So anyway, that was an insight of how the mixer currently is. Were there any more mixer insights on the way? Yeah, so there was some debug info in this left corner. Not terribly exciting, but that first hex number actually represents two values. The high nibble, sorry, is the currently selected column, which is, sorry, my headset conked out again. And so right now we're on column 0, and so let's say that's HDMI left. But if we were to get column 1, if we're 1 showing in this nibble, then that means we're currently selecting column 1, the HDMI right, and so on. This will be 2 and 3 and so on. And the low nibble itself is which row we're on. So SID L would have 0 here. If we were highlighting SID R, it'd have a 1 here. That'd be if we're highlighting phone 1, that'd be a 2 and so on. And the second hex number represents the coefficient index of the current selection. So currently we're highlighting this one where SID left input meets the speaker left or HDMI left. And you're seeing this C index value of 0, 1, which points to this the low byte of the coefficient value. Yeah. And yeah, it's always going to show that low byte value. So even if you jump and highlight SID right on HDMI left down here, it'll say 0, 1, 2, 3. This would become 3. So it'll always show the low byte. And if you ever need to know the high byte, yeah, just whatever value is here, -1, and you'll get the high byte of that coefficient index. So yeah, and the coloring scheme they've used here is that The currently selected coefficient index is shown in white, what we've got here, and all outputs on the same row are also shown in green. So this is the row we selected, so the other outputs are shown in green, and also the other columns, or sorry, the other rows in that column are also shown in green as well. So anyway, back to the drawing board. We know that I tried changing the on-off of the amp chip via that mixer coefficient. It didn't help. I mean, I did see it turn off, but it didn't make any music, and still no sound from the internal speakers from what I heard from Hojo. And so then it became looking at that, how it was set presently. And so, okay, that bit is turned on. It turns on this amplifier enable signal. But what does this amplifier enable signal do? Now we've got to sort of follow that journey through the VHDL. Yeah, let's follow that journey. And I thought I'd sort of animate this. As I go through VHDL, I tend to draw these ASCII block diagrams to help sort of guide me visually with where I'm at, and because one VHDL component resides in another, it's hard to keep it all in your head. But yeah, after we do this visualization with my ASCII diagram, we can look at a bit of the code and follow the journey there too. So yeah, this was a big chunky ASCII sort of diagram I drew to try and guide me through this. But let's start. It's a lot of VHDL files, but let's start at this audio mixer file and try and grasp what it's trying to convey. I was curious about it because this is where that amplifier enable signal is being outputted from. So the FE register number is being hit, and it's turning that amplifier enable on, for example. And beyond that, audio mixer resides inside another VHDL file as a component inside audio complex. And so I then have to study, how does audio complex make use of this amplifier enable signal as it comes out? And in many of these layers, you'll find it just passes it through to the next outer layer. It doesn't do much with it. It just passes it on to the next layer, which is IO mapper VHDL. So IO mapper VHDL houses audio complex. It's inside there. And again, IO mapper doesn't do much with it. It just passes it on to the next layer above, which is machine VHDL. Didn't do much there, except it renamed the signal to amp ST, so amplifier enable here has been renamed to amp ST. Okay, and then what does that do with that? Not much really, and it just passes it on to the next layer, which is the outermost layer of the VHDL, if you like, this Mega 65R3. And here it's been renamed again to I2SSD. But then since this is the final layer, then there's this, what is it going out to the FPGA pins as? For that, you have to look at this Mega 65R3 XDC file, and that will tell me this is pin F18 on the FPGA. So that way I can learn this signal from inside this VHDL amplifier enable. Where is it going out to from the FPGA? So yes, these XDC files, that's where the VHDL meets the schematic, if you like. So looking inside our, oh, actually, I said I was going to study this. Yeah, all right, we can study that journey a bit manually. Let's look at code. So I'm in my Mix65 core source VHDL folder. I'll open audio mixer VHDL, and in here I guess I'll look for amplif, if I can spell it. Why can't I find it? Have I changed anything? Oh, yes, I have. I can't follow this journey because I've changed my code base to new stuff. Which branch am I on? Yeah. Okay, how about I check out the development branch, which I haven't updated to the latest, and I try again. Okay, here we go. Now, because I've removed it from here in the latest stuff, but yeah, it's still there in the old stuff. So yes, we see coming out of this audio mixer component is an amplifier enable signal. And if we want to see who's reading that signal, we go to the layer that contains this audio mixer, which we saw before was, I think, audio complex. So if I open audio complex, and if, sorry, spelled it wrong, audio complex. If I look in there, I see up here that this audio mixer is in audio complex, and its amplifier enable signal goes to a newly named one inside here called AMP-SD. So yeah, so AMP-SD got renamed here actually. But anyway, then it goes out of this one, and the one that contains this is IO mapper, the next layer. So edit IO mapper, VHDL. Oops, I've already got it open, is it? Just open anyway. So here it wasn't called amplify enable, it's called AMP-SD, right? So yeah, it comes out of here as well, but to see where it's actually coming out from. So this component is the audio complex component sitting inside IO mapper VHDL. So taking a look there, you see it's just routing AMP-SD inside this component, audio complex, out to AMP-SD inside IO mapper component. And then we move out to the next layer. Where's that go? To machine VHDL. Okay, edit machine VHDL. And if I look where the IO mapper is in there, okay, IO mapper is in there. And if we look underneath, we'll probably find AMP-SD in there somewhere. I'll just search for it to get quickly. Yeah, and it also has an AMP-SD leading out. So in machine VHDL instance of IO mapper. Okay, so it's coming out of here too. And then we go to Mega65R3, Mega65R3 VHDL. And if we look for AMP-SD there, hopefully it's there. And we can see it's been tied to another signal called I2SSD. Okay, and the component this is a part of is called the machine. Yeah, okay. Going back there. Oops, where was I? Yeah. So if I look for I2SSD, it's an output out of this Meg65R3 file. So if it's an output out of this highermost VHDL, the only way we know where it goes to is that XDC file. So we can edit the Meg65R3 VHDL, oh sorry, XDC, sorry. And in here, if we were to look for I2SSD, oops, sorry, I have to switch it along here. Yeah, and we see it's I2SSD is tied to pin F18 on the FPGA. Okay, so that's how you would undergo such a journey, just in case you're ever curious yourself to follow one of these signals and see how it goes out of the system, out of the FPGA. So yeah, in that Mega65 R3 XDC file, we found out that the I2SSD line, it's equating to pin F18 on the FPGA. And if we do start looking at schematics, we see pin F18 has a, a different name. Sometimes you will find out that the people that made the schematic gave a different name to what was the last thing named inside the VHDL. But anyway, now that we've gone that far, we have to follow that journey through. We're outside of the FPGA, so now we have to look through the schematic and see where does that signal go to out of the FPGA. So if you ever need to look at the schematics, they're in the Mega65 book PDF. If you need a copy, go to mega65org.docs. Maybe I'll visit that now so you see when you visit it where to find it exactly. So here we've got PDF manuals of the individual manuals, user guide, reference, and so on. The one you're after would be the complete compendium, I'd say. I tend to go for that because that's got everything. So I download that one over here for the latest. It'll always have the latest. There's always changes being made and improvements and additions. So yeah, if you ever need the latest, come here and just grab it that way. Yeah. So, yeah, this is our last clue so far. This coming out of the FPGA on pin F18. This NSD audio signal, as it's now called, what used to be called amplifier enable, back inside our VHDL. So yeah, this we've found that association. But yeah, we'd have to search through the schematic, maybe use Control F. What is this NSD audio connected to? And you'll find it's connected to the audio amp chip. So this SSM2518 chip, and it's coming in here, going to its hooked up to its SD or inverted SD line. And we also see that this chip is hooked up to the internal speakers coming to J19 and J22. Yeah. So it seems like we're in the right place. And yeah, that's the ones we saw before. Oops, sorry. Yep, that's the SSM2518 and the two speaker connections we have over there. So now it's time, now that we know it's going to this SD line, we have to learn about this AMP chip, what this SD line is supposed to do over there. And that's the time of Googling for the manual and finding, reading the PDF I learned, okay, this line is meant to power the chip on and off. There's a list of pins, and yes, inverted SD means power down control. Okay, good to know. And I also confirmed it this way, like I tried to find where the SD line was on the chip, and I found another point where I could safely put my oscilloscope probe, and I tried to see if I could turn that line on and off via turning that mixer coefficient on and off. And yeah, indeed, I did see this line go on and off. So that was some comfort, at least, that the chip is being turned on and off successfully, but it still wasn't doing its job. So that's when it came time to think about, should I install, get the parts to install these internal speakers myself. And so yeah, and I'll just share with you the bits and pieces I got. I got this crimping tool after a video sort of walked me through how to use it. I've never used such a crimping tool before. JST XH connectors. I needed to buy parts to suit the sort of connections to be made, these housings, the contacts needed. I tended to buy a few extras because I thought it's my first time doing it. I'm probably going to stuff them up. So at a bare minimum, you can take my quantities, but if you feel like you might make some mistakes, you can buy a few more. The two speakers that needed and the screws that I needed, I think I went for like 5mm style screws and screws that were more suitable to plastic. I don't know if you need to go to that level of detail. Maybe just ordinary screws that are about this deep should be okay. And I also bought two chunky capacitors to get rid of the DC bias I found later. Um, but yeah, it took a while to get those parts in. I think that maybe 2 or 3 months before they came in. So in the meantime, I thought, can I just get any old speaker? I went down to the electronic shop and they had an 8 ohm speaker, a little different from the ones that I'd ordered, which were 4 ohm speakers. But I thought, yeah, that'll do. And but to hook it up to the J19 port, I used these things I'd never heard of before, parrot clips, to sort of pull them across and sort of just clip them onto these things, which was yeah a nice sort of temporary way to do it before I could get the connectors ready for this. But yeah, I did all that. I turned the amp chip on and still no sound coming from it. But why not? And yeah, I didn't have any idea at that point. So what's this? Yeah, I'd assured, yep, that signal, it's routed correctly to the amp chip. It is turning on and off, but still no sound coming out. It just meant I had to read this amp chip's entire PDF and try and figure out, well, how is it meant to work? And that was a challenge. It's 48 pages long, and to get familiar with it, it takes a while. And understanding how we had chosen to configure it and decipher that sort of configuration of it. So how does the amp chip work? In a very high level view, the chip has two communications pathways with the Mega 65. And yeah, so the amp chip has its outputs there. The first way Mega 65 communicates to the amp chip is over this I2C bus. So this is like purely for configuring settings on the amp chip. So maybe the Mega 65 wants to say, hey amp chip, turn the left speaker's volume down. That kind of configuration goes over this bus. Or maybe it might say, oh, I'd like to read that information back, please. What did I last set the volume setting of the right channel to? Yeah, and you could make that query there and come across the I2C bus. There's also this I2S bus, and this was for streaming that audio across, the left channel and the right channel in a digital sort of a serial form. And yeah, and that amp chip will then convert it into an analog signal and pump it out these two pathways. That was a block diagram they provided. As for the buses, it's hard to see them here, but SDA, SCL are the I2C bus lines here, and the I2S bus lines are across over here. So I guess this is for configuration stuff going in this way, not part of the full chain here really, but maybe it impacts it in some way. But the chain of the digital audio coming in here is more this pathway here, the left-right clock signal, the bit clock, and the serial data of those sample like values, I guess. And yeah, that's the I2S path over this way. So that also I didn't have much inkling of I2C except that it's some sort of serial protocol. And yeah, I had to Google that and watch YouTube videos. That was a nice one here to help me better explain. Yeah, and that'll explain it better than I could. And it stands for Inter-Integrated Circuit, I learned. And it's a synchronous serial protocol, which it means it has a clock telling it what to do. So there's this SCL line, the clock, and SDA, where the serial data is pumped through. And the idea, it allows one controller, which in the old days was called master, but not so much these days, to talk to different peripherals, like which peripherals was the new name and slaves was the old name, just for context. And yeah, as for how these sort of you know, the clocking and the data bits over serial lines, um, there's a sort of way to write things. Like if you have a write code, Mega 65 wants to write something, it would follow some sort of pathway like this, which I can explain later. And then there's a read pathway to sort of say something like that. Maybe I can decipher some of it. Sort of like, okay, Mega 65, I want to talk to this I2C device at this address, and the actual I/O register on this I2C device I'll just specify here. And oh, this is a write. Yeah, sorry, this is a write. So then the value I want to write to that I2C register is here. And this read one is even longer. This is the Mega 65 saying, I want to talk to this I2C chip at this address, and the subaddress is I want to read this particular register, register one or something. And then I think this is the chip answering back and saying that, okay, here's the data you wanted at that IO address, and yeah, along those lines. So how is I2C used on the Mega 65? Yeah, we've got these SCL, SDA lines too. And what kind of I2C peripherals do we have? There's different things: Grove, Serial, EEPROMs, RTC, AMP chip. And I'm probably oversimplifying here because later on I learned that there are multiple I2C buses on the Mega 65, and some are isolated from one another. Um, and which devices are on the bus can vary depending on which revision of the board you have, R2, R3, R6, or Megaphone. So for R3 is the only one with this AMP chip, let's say. And yeah, in truth, yeah, Meg 685 has multiple I2C buses. I think there's even a unique I2C bus for like HDMI, maybe because they don't want it interrupted by any other comms, I suppose. But yeah, so what can so yeah, I guess I2C bus being on this side, we're focusing on here. And yeah, that's dictating we want to talk to this chip at this address. So I2C address 34 means, yeah, I want to talk to this chip, and that's why this chip knows you want to write to its registers or read from its registers. So what kind of AMP chip configurations are permitted, over the I2C bus? If you look at the manual, it's got this big long list of hard to get your head around, some sort of reset logic on register 0. Maybe the more fathomable ones are the left volume control. So if I want to talk to the chip's I2C register 5, I can set the volume for the left channel, or register 6, I can set the volume for the right channel. Those ones are easy. There's some mute settings if I want to mute certain things. Can't remember, the right mute is this bit, the left mute is that bit, or other kinds of things there too. Yeah, but it's too long for us to visit each one and learn. But I think the biggest challenge is these choices here impact certain signals that you feed into the chip called M clock and B clock. I think B clock is bit clock, maybe M clock can be deemed master clock, I'm not sure. And yeah, our config choices will impact what you're meant to feed into these input pins. For a start, any of these registers you're interested in, the manual will elaborate on them. Let's say if you're interested in register 0, there'll be a page in there, say register at address 0 is this, and those bits that I mentioned here, S reset and whatever, MCS, you'll see they're elaborated here, S reset and MCS master clock select, blah, 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 blah. And then there's even a more elaboration underneath where they sort of say in more verbose detail, S reset does this, 0 does that, 1 does that, blah, 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 blah. Yeah, it's a lot to take on. But then it's a thought of how have we configured the AMP chip ourselves. And what I noticed is it depended on which era of the project we were looking at. So in the past, when Gardner's was working on the audio AMP chip, I think he started out on the Megaphone. So that was his first area of focus, get this AMP chip working on the Megaphone revision 1. And he got it working. And so that was a source of information for me. I was curious. Well, you had it working on the megaphone, so maybe I can read your blog post and learn a bit on how you got it working there. And so that was one source of understanding I got was from there. But yeah, it's quite a head spin, and it's hard for me to convey what I learned from that, apart from visiting my own log notes, which you're welcome to do. It's day 472. If you visit that, you could dive in and start reading what I'm trying to comprehend of these things. And yeah, big long journey. I'm not sure how much I can convey to you, but best I can recall is that a key part of the way it was configured back then was register 0, this reset and control stuff on address 0, had this no B clock line. And we had set that no B clock line to the value of 1, which meant here M clock pin is used as a bit clock source. No B clock pin connection is needed. So I guess the M clock you feed becomes the bit clock itself, something like that. So that became a key part of this configuration that we had done for this AMP chip. So yes, for R3, we only provided an M clock into the chip, and we always set this B clock line to 1. It was hard coded to 1. It never toggles up and down. But what I noticed in more recent times, the implementation side of our VHDL had changed M clock and B clock to different things, and it no longer worked for R3 the way it did back in the blog post days. And what I later learned is that, yeah, this logic was updated later when the R6 board was worked on. For the R6 board, the AMP chip was removed and instead a DAC chip was put in, and the DAC chip hooks up to the headphone socket instead. So yeah, that caused the M clock and B clock usage to change. But this M clock, it's yeah, I struggle to remember everything. All the reading it's a very tricky PDF to comprehend. I think one aspect of choosing the M clock relates to getting your head around this big table in the manual. And even now looking at it, it's overwhelming for my eyeballs. Um, how to convey it? You can see there's a choice of what kilohertz are you planning to feed into the chip. So do you want to put 44.1 kilohertz audio in? If so, you're going to have to make some choices here. You're going to have to make an M clock choice, and you're going to have to make a what do they call this? An MCS bit field choice. And that's pretty difficult choice to make. How do you make such a decision when there's one known thing and two unknown things? The two unknown things, what M clock do I need? What MCS setting do I need? And I struggled to comprehend it. But at least day 472, you can follow my journey of how I started to piece it together. I looked at the MCS field and I tried to learn more about that. This part here, I'm trying to look at Paul's blog post where I look at the settings he applied to those I2C registers and try to get a feel for what he was trying to do with his settings. But further down, I looked at the sorry, my headset conked out again. I looked at the default values and how his settings differed from default values. And there was a part inside the Hippo boot where I see how does Hippo boot apply these, well, its chosen default I2C settings for the AMP chip. And yeah, these were the kind of points where I found that. And I've kind of annotated them as well. This was an interesting part where I saw there were separate sections for the megaphone and its default I2C settings for the AMP chip. And the MEG65R3 had a unique set of settings too that were different. And yeah, here's a point where E1 and E2 are set to 20, which turns out to be a very high volume setting. It was blasting setting, and but the default was meant to be 40. So yeah, you can see the kind of choices he made and how they differed from the defaults if you study that part. But I think the penny maybe dropped a bit deeper down. Okay, here's me looking at MCS and trying to fathom what's this choice actually doing. There's this multiplier stuff happening, and even this was confusing. But then I started doing some of the math, like I, 256 times FS and the M clock, and I think I got. Oops, sorry. Um, I started highlighting it and started noticing that there were sort of groupings of these that were differing in their calculations. So let's say if that maths is right, and if I'm looking at this first one, 256 times some fs is going to equal 2.048 megahertz. Oh, sorry, no, 8 kilohertz. Oh man, it's a head spin still. Uh, okay, no, I still can't follow it. 256 times 8 kilohertz is 2048 megahertz. Okay, but that's only if fs is 1. Yeah, is it? Yeah. So, but then it kind of changes here. So let's say if we do it for the stuff I've highlighted in blue, 128 times fs. Okay, so 128, okay, times 16 kilohertz is 2. Okay, all right, I'm even more confused then. But yeah, getting my head around this was difficult, but I seem to have noticed some grouping pattern here, which my mind can't fathom anymore. Um, yeah. But later on, yes, later on, um, do, 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 do. I contacted, well, the analog devices, the people that make the chip have like an online forum where you can ask questions. And I did ask a question to get some feedback on what I was witnessing. And he kind of explained it a bit better. So, yeah, he said what I was seeing was a kind of a selector that's being made here that isn't being conveyed so well in the diagram. You're selecting between either this group or this group or this group or this group. And that selector, he later on mentioned, is on another register on address 2, this bit field called FS. And what it's trying to say with this is that if you're interested in an input sample rate in this range, you have to set this FS bit field to this value, like 00, 0. But if you're interested in like 16 kilohertz to 24 kilohertz range for your waveform, then you have to set FS is 1. And somehow, maybe that makes this diagram more palatable, but even for me, that's still, I think I later annotated it differently to try and get my head around it. I changed this to, I've annotated this differently. I've kind of made this everything here divided by 2. And that FS value, I called now an FS multiplier, that one that he pointed out here. I called that a bit like a multiplier. And so yeah, it's hopefully that kind of conveys. Oh, and I've said FS multiplier is 1 or 2 or 4 or 8. So I'm trying to convey how I now read the table. But yeah, looking at it now, and I even re-annotated the table to try and convey that to you're choosing which group of things you want equals what FS bit field setting to do. So if you were to pick 44 kilohertz, you need to pick FS mult, and and then I guess that means if you want, or maybe it's a choice of which megahertz or which M clock rating you're capable of making, and then deciding the MCS bit field value accordingly. Yeah, but it's quite a head spin to get around. That's as best as I can convey it back to you. But if you ever have to dive in there, I hope it helps a little bit. But yeah, there'll be plenty more digging to do on your own part to get your head around it too, I'm sure. So how does the Mega 65 talk to ITC devices? There were some hints of this in Gardner's blog post there, and there's also some information in the Mega 65 book. But it seems like different I/O address ranges are now kind of mapped to different I2C devices and their I2C registers, if you like. So here he's kind of described some of it in the manual. Yeah. Oh, and these ranges can vary depending on target. Are you on R1 or R2 or R3 or R6? Yeah. So yeah. Um, as for the exact specifics of the ranges, you can look in the IO mapper VHDL file, and you'll see there for megaphones, there's this assessment: am I a megaphone R1 or megaphone R4? If so, then I'm in this D70 something something range, which you see mentioned here, megaphone R1. Their registers are in this range. So yeah, ICC peripherals are there. But for the R2 board, there's another chunk in this IO mapper VHDL file. If target is R2, then my HDMI stuff for I2C is in the D72 range, which is mentioned here. And yeah, but the peripherals are at the D71 range, which yeah, is mentioned here too. Yep, I2C peripherals for R2. Yep, that's good. And HDMI D72. Yep. For the R3 boards and above, there's another section said if target is R3, R4, R5, R6, then our peripherals are in this D71 range, just like the R1, I think. And our HDMI I2C is in the D73 range, all the registers for that. Right now it says it's future I2C, but no, that's been taken up. And also the Grove connector is at the D74 range, which hasn't got a mention here as yet. But what that means is though that, how do I put this? You saw before that I could type commands. I don't have any good way to do this. Is there a command line? Um, I don't really have it hooked up to the Mega 65s. It doesn't really matter. But it's more trying to say, you remember in the UART monitor, I would type in commands like set an address to a value. It would mean that certain I2C registers, you could hit them in these ranges. So let's say, I forget exactly now, FFD6 something or other. The FFD, I've completely forgot. Maybe it's in the Discord. Sorry, I have to jump to Discord and remember what it was again. Where's the picking parts for that thing? Search for what was it called again? Left speaker, right speaker. Just speaker. There was a place where I had. Nope, I cannot find it. It was FFD something, I'm sure, but left, maybe just left. Here we go. These settings. So, yeah. Sorry, get that command prompt here. So in the UART, actually I can connect to Mega 65. Yeah, I'll do it. So if I go to, because my Mega 65 is turned on, and if I just exit out of here, Mega 65 debug. I forget which port I'm on. TYS, maybe S4. It's not that one. Oh no, I'm not plugged in. Oh no, I can't do it. All right, but if I were, I have to just open a new one. I would be typing in Meg65 set a certain address, let's say FFD71E1 to a certain volume for the left channel of this amp chip, and I would enter. And of course, this isn't Meg65 debug, but yeah, that sort of thing would happen. Just close that one. That's dead. And if I wanted to set the right channel of the amp chip, yeah, I would set the volume that way. For some reason, lower values are louder and higher values are quieter. So that's that. And yeah, so what I was trying to convey earlier is that this mapping of I2C registers is done that way, where you hit, did I get rid of that thing? You hit the address on in the IO map, the memory map, and behind the scenes, the VHDL will do all that I2C sort of serial data comms that do all the, I want to talk to this I2C chip, I want to talk to this register, I want to write to this register on that chip, and I want to send it this value. So yeah, the VHDL handles all of that serial comms pathway of the I2C for you. All you have to do on your end is to know which register to hit on the memory mapped area. So quickly, what is I2S? I learned it's not a typo of I2C, I should say. I thought it might be, but it wasn't. And yeah, online resources will explain this better than me. Is Wikipedia if you're interested. It stands for Inter-Integrated Circuit Sound. And yeah, it's just another synchronous serial protocol consisting of 3 lines this time. The bit clock, the left-right clock, which kind of says now the bits coming in now are for the left channel, and now here's the bits coming in for the next sample of the right channel. And this bit clock, the left-right clock toggles back and forth saying here's a sample for the left channel, here's a sample for the right channel, like that. So yeah, 0 is left channel, right's right channel. And serial data is the serial stream that's pumping out, all that left channel sample stuff, on, off, on, off, on, off, so on. First the left stuff, then the right stuff. And how does the Mega 65 pass streaming data? I'll keep this brief because I did dive into it, but the problem wasn't in that area, so I don't feel like it needs to be digging too deep. But if you're interested to dig in further, at least you'll see where you should dig. So outside of the Mega 65, there sits a 100 megahertz clock chip, and that gets fed into the FPGA and comes to this clocking VHDL component, which can divide that clocking chip into various other divisions that are needed by the system. One of those divisions is dividing it down into 40.5 megahertz, and that gets passed into this I2S clock. And so that takes that 45 megahertz and divides it into whatever the logic in here dictates to be what should be the M clock value to be. And so that dictates this M clock speed that goes to the amp chip. But the other aspect is with I2S is where's this data coming from, the serial data for the samples? That's coming from this I2S transceiver VHDL, and that is responsible for this PCM out signal that goes all the way to audio S data, which is all the up and down serial up and down on the S data line for left channel and then right channel. But then it's also the one that is saying the left-right clock. That's this, is it? Oh no, this is coming from the I2S clock. Yeah, that's the output here, going to the left-right clock out there. But this left-right clock is also going to the transceiver. Okay. And as for the B clock, here's where you see inside Mega 65 R3 VHDL. It's been hard-coded here to always be high or 1. But then you'd be curious, okay, this is how it pumps out this serial data, but where does it get this audio data from to turn it into serial data? And that's coming out of the audio mixer here. So here you see it's taking output 0 and 1, which are equating to what we saw as the speakers or HDMI left and right. And it's bringing them up to speaker left and right here. And some logic in here is breaking that down into some serial up and down, and out it goes. So yeah, if you need more details, yeah, just dive into those files and you'll get more of the story there. So the other aspect of this project was I'd heard stories of the speakers heating up, and yeah, some users reported that. I think ADTBM reported that, maybe Hojo as well. So I tried checking with some my temperature sensor on my multimeter, and I put the probe on the metallic part there in the middle. And yeah, and over time, yeah, I did see the temperature increase. It was a cold morning that day, I think about 14 degrees. And yeah, over time, how long's that? Maybe over 30, 40 minutes, it ramped up slowly to about 29 degrees. So not super hot, but that's on idle, there's no music playing. And what I noticed on the scope was it's because even on idle, there's like a DC offset that keeps going to the speaker. So there's constantly power being put on it and a current flowing through it. Yeah, inevitably that's heating up the speaker. So yeah, I tried my best to remove the DC offset with a capacitor. I'm no sort of electronics expert. I did study a bit in university, and uh, it probably wasn't the best place to put it. I had to put the capacitor on the output side, after it had been amplified, which means you have to use a bigger capacitor, which isn't so nice. I mean, ideally, I suppose with an amp you should put the DC, sort of offset removal on the input side, so your capacitor can be smaller. But we can't do that anyway here because the input side for our amp chip is like a digital serial line I2 or I2S line. So maybe you'd have to put something in the VHDL to. But anyway, I did it this way. But then, yeah, what size capacitor to pick? I couldn't remember how to do the maths for this, so I had to watch an online video about RF filters. That's the one I watched. And around 1436, that's when they shared this formula on how to, well, they phrased it as in the cutoff frequency will be this if you pick this R and this C for capacitance and I guess the resistance of your speaker. And so I had to rearrange this formula to focus on what C I needed, shuffle things around left and right. So I shuffled it around. So the capacitor I need is, 1 divided by 2 times pi times the resistance of the speaker times the cutoff frequency I want. And I decided, let me try a cutoff frequency of 20 hertz. From what I heard, that's the lowest frequency human ears can hear. And so let's cut off everything underneath that as best as we can. So the speaker resistance was the 4 ohm one, and the capacitance, or impedance I should say really, the capacitance, yeah, that the calculation for this ended up, I've got my R, I've got of 4, I've got my cutoff of 20, I can then, do the maths here, and yeah, so the capacitance I need is about 2000 microfarad, and so I went to my electronics shop nearby and bought these 2200 microfarads, and I thought, yeah, that'll do. And I added the caps in series to my speakers, and yeah, the DSET offset is gone, so the speaker no longer heats up according to my temperature probe. Yeah, so that's good news. I do worry about, because I chose electrolytic caps, and those caps do have a polarity that apparently they can explode if you put them the wrong polarity, and I imagine with audio signals they can be positive sometimes, negative signals sometimes. But anyway, so far my caps haven't popped, so I'm happy about that. And yeah, that's how I set it up there. I think I described it earlier, that these caps are now in series with the speakers here, one for each. So yeah, to wrap up the reasons and the fixes, I feel the ASIC boards had dropped the audio amp chip and they added that DAC chip instead, which goes to the headphones. And in the process, they modified that M clock and B clock signals to suit the DAC. And those changes were made to this I2S clock file. So my solution was I made a new I2S clock R3 VHDL file, and that contained an older revision of this I2S clock logic that suited the R3 and its amp chip. And I also got rid of some of the amp chip routing that went to the mixer coefficients. We don't need that anymore. And so now it's routed the proper way via this IO register D6FE on its bit 0. No need to fiddle with the coefficients of the mixer anymore. And yeah, I got rid of the DC offset with the capacitors. I also updated the config screen with a nicer name to avoid that confusion in future. So let it say R3 audio amp chip, so there's no sort of mix up in what it's for. So yeah, demo time. What am I? So yeah, I can show you a video of the audio playing through the internal speakers. So okay, just showcasing how the amp chip changes have progressed. So I'll use this one, the latest core for this build. I've muted the TV to ensure that all sounds are coming from the speakers only. So if I pick intro this one, definitely coming from the speakers there. Let's go back out. Go to introduce 2. Yeah, coming from the speakers there. And back out. Introduce 3. All good there. And introduce 4, which is the loudest for some reason. Super loud. Okay, so all good there. And also maybe just to highlight the way I connected things up. Oh yeah, I shouldn't have stopped that so early. Yeah, I know I talked about how that was all connected. That's okay. And the adjusted left-right volumes, I demonstrate that in this video.
So I thought I'd capture changing the volume of the amp chip. So to start disc 1, if I felt it was too quiet, I could lift up the volume of the speaker, the left channel, while I can set FFD 7.1 E1. Right now it's on 45, I can bring it up to 40. How much difference is it? FFD 7.1 E1, let's make it 30 instead. Yeah, it's a bit more significant difference. Let's make it 20. D7, it'll be even louder, super. Yeah. And I can do the right speaker, FFD7, 1E2, 20. Yeah, that's done. Yeah. One thing I observed though is when you set these, I'll just silence that for a second. When you set these, you could be tempted to do like set FFD7.1E1. You might be tempted to do 2 in a row, like 40-40, as in E1 set to 40 and E2 set to 40. What I found is that that doesn't work. It seems like only one of them kicks in, because each one of these is triggering the I2C sort of serial traffic to make that sort of information pass across. I want to set this I2C register to 40, and that takes time. So yeah, I found if you try and bash 2 of them at the same time, it doesn't give the system enough time to pass both messages across, and only one gets through. So yeah, that's why it's better, instead of E1 being 40, E2 being 40 all in one line, separate them to be like up above, E1 is 20, E2 20, so that'll give it plenty of time.
Okay, yeah, that's all I've got for you. So yeah, if you survived this long, thanks for watching, and yeah, I'll end the stream.